Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. This is my fourth class on vector spaces. This is a part of linear algebra course in Telangana state. In my previous classes, we have discussed about vector spaces and subspaces and some examples on subspaces and vector spaces. In this class, let us quickly recap the definition of vector space again and recap the definition of subspace. And today we will discuss about linear combination of vectors and span of vectors and some theorems on spanning set, and we will do some of the problems on subspaces. First, let us recall the definition of vector space. A vector space is a non-empty set V of objects called vectors on which two operations called vector addition and scalar multiplication are defined with the following 10 axioms. So it is a non-empty set V of objects. So you can take any of the objects, pens, pencils, etc. Anything you can take, chemicals, signals, everything comes under vector space, provided you will define two operations, one vector addition and another scalar multiplication, such that all the 10 axioms are satisfied. Those 10 axioms are: for all u v, w belongs to v. So these are the vectors or objects, and scalar c and d. Usually we take real numbers as scalars, but we can take the elements of any field as scalars. So these are 10 axioms. First one is u plus v belongs to v. This is closure property. And u plus v is equal to v plus u, commutative property. And u plus v plus w is equal to u plus v plus w, associative property of vector addition. And there must be a zero vector o in v such that u plus o is equal to u. And for each u in v, there is a vector minus u in v such that u plus minus u is equal to 0, additive inverse. Here it is called as negative. So these 5 conditions will form an abelian group with respect to vector addition. And this is scalar multiplication rule. The scalar multiple of u by c is denoted by cu in v, that is cu belongs to v. So the set is closed under scalar multiplication. And the 7th one is c times u plus v is equal to cu plus cv.
And the 8th property is that c plus d times u is equal to cu plus du, where c and d are scalars and u is a vector. And the 9th one is c times du is equal to cd times u, where cd are scalars and u is a vector. And finally, 1u is equal to u. If all these 10 axioms are satisfied in a set V, we can say that V is a vector space.
Vector space V is a subset H of V that has 3 properties. First one is the zero vector V is in H, and the second one is H is closed under vector addition. That is, for each u in V, u and v in H, the sum u plus v, vector addition u plus v must be in H, that is closed under vector addition. And finally, the third property is H is closed under multiplication by scalars, that is, for each u in H and for each scalar c, the vector cu is in H. It is enough to show that these 3 properties hold in a subset of a vector space V to prove that that subset H is also a vector space. Remaining properties either inherited from the original set, or the same can be proved using the combination of these axioms. All these things were discussed in detail in my previous classes. So with those things, let us move on to the today's class. So it is linear combination. So we are going to discuss about linear combination of vectors. Any sum of scalar multiples of vectors is called linear combination of vectors. Any sum of scalar multiples of vectors is called linear combination of vectors. Suppose we have only 5 rupee coins, then the transactions can be done in the multiples of 5 only. So 5 rupee coin is my V, vector V. C is any scalar. For here, for convenience, let us take the integer scalars only. So you can't have 0.5 5 rupee coin. That's why in that example, let us take only integer scalars only. Then all the multiples of 5. So you can make transactions in multiples of 5 only. When there is only 5 rupee coin in the world, you can't make a transaction of 7 rupees or 13 rupees. So all the multiples of 7 is a linear combination of 5. Similarly, if there is a 5 rupee coin and 2 rupee coin, you have two vectors now. So V1 is 5 rupee coin and V2 is 2 rupee coin. Then the allowed scalars are all integers. Suppose that the allowed scalars are all integers. Then you can make transactions of any integer. So if you want to make a transaction of 3 rupees, 5 minus 2. When there are only 5 rupee coin and 2 rupee coins in the world, still you can make the transactions of 3 rupees by giving a 5 rupee coin and taking back 2 rupee coin. Similarly, you can do any transaction with this, with the combination of these two, even negative numbers, negative integers. But you can't make the transactions of a fraction of a rupee. You can't make a transaction of 1 rupee 50 paisa with these two vectors. So the linear combination of 5 and 2 is entire integers, entire set of integers. When the allowed scalars are integers. This is to know the definition, to understand the concept of linear combination. But here, our scalars is a set of field. Usually, we are taking real numbers as our scalars. So even 1 rupee 50 paisa is also possible with 5. As I can take any scalar of any real number as my scalar here. So here, the vectors are different. I can take any colors. Colors are my vectors. So if I put some weightage to a color and some portion of another color, I will get another color. These are the combinations. So if all the colors are my vectors, you can took any weightage and the mixture will be another color with those weightages. All the possible colors will be the linear combination. That is the concept of linear combination. So mathematically, it is very simple to explain. Let V1, V2, and so on Vp belongs to V. So these P, there are P vectors, P objects in fact. There are P objects in our set V, but in vector space we call the objects as vectors. The set of vectors, these are the vectors, and C1, C2, and so on Cp are scalars. So usually we take real numbers as scalars. then the vector y defined by c1 v1 plus c2 v2 and so on plus cp vp is called a linear combination of vectors v1 v2 and so on vp with the weights c1 c2 and so on cp. So any possible vector with the combination of these t vectors is a linear combination. In fact, in a color printer, there will be only 3 base colors. By adding these 3 colors in different ratios, you will get different colors. So all the possible colors with the color printer are the linear combination of those 3 base colors. Those 3 base colors will be V1, V2, V3 to me. So C1 V1, C2 V2, C1 V1 plus C2 V2 plus C3 V3. This should be the resultant vector. That will be a linear combination of those 3 vectors. So similarly, we can take any object which is a result of linear combination of objects in the vector space. So this is the definition of linear combination. So hereafter we will use this result y is equal to c1 v1 plus c2 v2 plus so on cp vp whenever we know that y is a linear combination of these vectors. Next definition is span of vectors. Span of v1 v2 and so on vp. This is the set of all vectors that can be written as a linear combination of v1 v2 and so on vp. Linear combination is a single vector, resultant vector of the vectors in the vector space. Whereas span of vectors is the set of all such vectors. In the earlier example, all the multiples of 5 are the span of 5, span of the vector 5. Similarly, set of integers is the span of 5 rupee coin and 2 rupee coin in the real world, where the scalars are integers. But here there are some limitations that those scalars must be a field here. So the definition is much broader here. So the set of all vectors that can be written as a linear combination of v1, v2 and so on vp is the span of v1, v2 and so on vp. So we indicate the set by this symbol, span of vectors. Span of v1, v2, v and so on vp is the collection of all the vectors that can be written in the form c1 v1 plus c2 v2 and so on plus cp vp with scalars c1 c2 and so on cp. Mathematically, we write span of v1 v2 and so on vp as the set of c1 v1 plus c2 v2 plus so on plus cpvp such that c1 c2 and so on cp are scalars. So this is the formal mathematical definition. So any vector which can be written in this form is an element of span of v1 v2 and so on vp. So this is the definition of span of vectors. So with this definition, we can prove this small theorem. Theorems are previous experiences which can be used frequently in many problems to solve the problems easily. These are accepted results. So this theorem is, let V1 and V2 are vectors of a vector space V, and let H is equal to span of V1, V2. So here we have taken only two vectors. Then H is a subspace of V. So we have to prove that the set generated by these two elements, these two vectors V1, V2, is a subspace of V. So it is given that H is equal to span of V1, V2. Span of V1, V2 is named by H. And we know the definition of span of V1, V2. That is the set of C1, V1 plus C2, V2 such that C1, C2 are scalars. So to show that H is a subspace, we need to prove three properties. One, zero vector must be there. It must be closed under vector addition. It must be closed under scalar multiplication. So first of all, since V1 and V2 are elements of V, all the possible linear combinations must be in V. Since we have these two properties in a vector space, it is closed under vector addition and scalar multiplication. So if you add any two vectors, you will get another vector in that V only. If you multiply with any scalar, you will get another vector in V only. So after adding those two different vectors, you will be in V only. That's why span of V1, V2 is a subset of V. It is very clear, it is obvious. So now we are going to discuss about the three properties of the subspace definition. The zero vector O can be written as 0 V1 plus 0 V2. Already we have seen the properties of vector space in which 0U is equal to O. So 0 V1 is O and 0 V2 is also O. O is my zero vector. So for the convenience to distinguish the scalar 0 and vector 0, I am calling it as O, as we are taking UVW as our vectors. So 0 V1 is equal to O, zero vector, and 0 V2 is also O, another zero vector. So O is zero vector plus zero vector. So zero vector O can be written as the combination of linear combination of V1 and V2. Here zero vector is written as a linear combination of V1, V2. Linear combination is nothing but the form C1 V1 plus C2 V2. Here I have chosen C1 and C2 both as 0, scalar 0. So zero vector is written as a linear combination of V1, V2. So zero vector is in the span of V1, V2. Span of V1, V2 is nothing but H. So O belongs to H. To prove the closure property of vector addition, Let us take two elements in H, that is span of V1, V2. Since U is in the span of V1, V2, it can be written as a linear combination of V1, V2. So U is equal to S1, V1 plus S2, V2, where S1, S2 are two scalars. Similarly, W is also in the span of V1, V2, so it can also be written in the form of a linear combination, that is C1, V1 plus C2, V2. Here I have taken another two scalars, T1, T2. So W is equal to T1, V1 plus T2, V2. So these two can be written in these forms for some scalars S1, S2 and T1, T2. Then U plus W is equal to U is S1, V1 plus S2, V2 and W is T1, V1 plus T2, V2. This is equal to S1 plus T1, V1 plus S2 plus T2, V2. We are in a vector space V. In vector space V, we have associative property, commutative property, and distributive laws. And using all these laws in a vector space V, we can rearrange these combinations. We can rearrange this addition as this one. So now U plus V is in the form of some scalar multiplied by V1 plus another scalar multiplied by V2. So it is in the form of C1 V1 plus C2 V2, where C1 is equal to S1 plus T1 and C2 is equal to S2 plus T2. So I can say that U plus V is in the span of V1 V2, that is H. So this belongs to H. Therefore, H is closed under vector addition. I have taken two elements in H. I got U plus W is in H. I got the sum of those two vectors is in H. So H is closed under vector addition. So similarly, we can prove that for any scalar C, Cu is equal to, that is C times U is S1 V1 plus S2 V2. That is equal to CS1 V1 plus CS2 V2. By using the properties in a vector space. We have distributive laws there. We have ninth property, distribution of scalars. Using all those properties, we can write this is CS1 V1 plus CS2 V2. Here CS1 is another scalar. Let us call it as C1, and this is C2. This is my C2. So it is again in the form of C1 V1 plus C2 V2. So it is a linear combination of V1 and V2. So it is in the span of V1 V2. Span of V1 V2 is nothing but H. So this belongs to H. Cu belongs to H. So H is closed under scalar multiplication. So we have proved all the three properties of the subspace. First we proved that H is a subset of V, vector space V. We discussed about that. Later we proved that zero vector is in H and H is closed under vector addition. Now we prove that H is closed under scalar multiplication. Therefore, H is a subspace of V. So span of two vectors is a subspace of V. We can extend this concept to any finite number of vectors. So this is the next statement. If V1, V2 and so on Vp are vectors of a vector space V, then span of V1, V2 and so on Vp is a subspace of V. Let H is equal to span of V1, V2 and so on Vp. Then again, as earlier we have discussed, span of V1, V2, Vp is the linear combination of these vectors, and by the properties of vector space, this must be a subset of V. And since O, the zero vector, can be written in the form 0v1 plus 0v2 and so on 0v, as we have seen in the case of two vectors. So it is the linear combination of all these vectors. Zero vector is the linear combination of all these vectors. So it is in the span of v1, v2, vp. So zero vector belongs to H, the span of v1, v2 and so on. Let uv belongs to H, then u is equal to. Let us prove that vector addition is closed. To prove that, we have to take two elements in H. So H is the span of v1, v2, vp. So each vector in H is a linear combination of these vectors. So u can be written as s1v1 plus s2v2 and so on spv. Similarly, another vector w also can be written as t1v1 plus t2v2 and so on tpvp for some other scalars. So here s1, s2, sp and t1, t2 and so on tp are scalars. So now u plus v is equal to this one s1 v1 plus s2 v2 and so on sp vp plus t1 v1 plus t2 v2 and tp vp. And by using the properties of a vector space, since all these are elements of that vector space and these are s1, s2, sp and t1, t2 and so on tp are scalars, by using the properties of vector space, we can rearrange them in this manner. T1 plus T2 V1 plus S1 plus T1 V1 plus S2 plus T2 V2 and so on SP plus TP VP. So now, since S1 plus T1 is another scalar, S2 plus T2 and so on SP plus TP, these are all scalars. Now it is in the form of C1V1 plus C2V2 and so on CPVP. So now U plus V is in the span of V1, V2 and so on Vp, which is denoted by H here. So U plus V belongs to H. We have taken that U and V are elements of H, and we concluded that U plus V is in H. So H is closed under vector addition. Now let us prove the third property. For any scalar C, Cu is equal to C times U. U is nothing but S1V1 plus S2V2 plus so on CPVP, SPVP. That is equal to C times S1V1. By distributive law, we can multiply this C with each element, with each component. And now CS1 and CS2 and so on, CSP are the new scalars. It is also in the form of C1V1 plus C2V2 and so on, CPVP. So it is a CU is a linear combination of these V1, V2 and so on, VP. So CU is in the span of V1, V2 and so on, VP, which is nothing but H. So CU is also in H. So H is closed under scalar multiplication. So we have proved all the three cases for these finite vectors V1, V2, VP also. So we can conclude that span of V1, V2 and so on, VP is a subspace of V. So now we got a new chance to prove a set is a subspace. It is enough to show that it is span of some vectors. First, to show that it is a vector space, we need 10 axioms. If there is already a vector space and we are dealing with a subset of it, to prove that it is a subspace of V, we need only three properties, including that should be a subset, of course. We need only three properties: zero vector, closed under vector addition, and closed under scalar multiplication. Now, after these theorems, these statements, we can conclude that it is enough to show that a set is span of some vectors of a vector space, to show that it is a subspace of that vector space. So it is a single step verification. So these subspaces can be regarded as subspace spanned by vectors. We call span of V1, V2 and so on, VP, the subspace spanned or generated by the vectors V1, V2 and so on, VP. For any subspace H of V, a spanning set for H is a set V1, V2 and so on, VP in H such that H is equal to span of V1, V2 and so on, VP. This is the spanning set. Spanning set is the combination of all vectors. So let us do some of the problems based on this concept. This is the first one. Let H be the set of all vectors of the form A minus 3B, B minus A, B. This is a 4 tuple where A and B are arbitrary scalars. That is noted in the set notation. Let H is equal to set of A minus 3B, B minus A, AB, ordered 4 tuple such that A and B in real numbers in R show that H is a subspace of R4. To show that, we use the previous concept. So let us prove that H is generated by some vector in R power 4 or R4. It is given that H is equal to this set. The given hypothesis is carried to here. So if this set is written as a column vector, this can be written as H is equal to set of a matrix, column matrix, A minus 3B in the first row, B minus A in the second row, A third component in the third row, fourth component in the fourth row, such that AB belongs to R, the set of elements. So this is the column representation of the given vector. Then any arbitrary vector u in H, so any randomly chosen vector in H can be written in this form. U is equal to A minus 3B, B minus A and AB. And this further can be written as A times column matrix 1. Here it is A. So here 1 minus A. So in the second row we have taken minus 1. Third row it is A here. So that's why it is 1 here. There is no A in fourth row. That's why it is 0. Plus B times minus 3, 1, 0 and 1. So each u in H can be written in this form. So if we take these two as our vectors, that is if v1 is equal to 1 minus 1 1 0 and v2 is equal to minus 3 1 0 1, we can write each u as a times v1. You have seen that this a times this is v1 and this is v2. So u is equal to av1 plus av2. Now it is a linear combination of v1 and v2. U is a linear combination of v1. So the set H can be written as set of av1 plus bv2 such that AB belongs to R. This is nothing but span of v1 v2, where v1 is equal to this vector. This is the v1 and this is v2. Where v1 and v2 are denoted by this one, the problem given is the space given in the problem can be written as that is equal to span of v1 v2. So now H is a linear combination of these two vectors. Each element, each vector in H is a linear combination of these two vectors. But here v1 v2 both are in R4 since it has 4 rows and 4 elements. So v1 v2 are in R4. As per our previous theorem, previous statement, we know that if v1 v2 and so on vp are vectors of a vector space V, then span is a span of those vectors. Span of v1 v2 and so on vp is a subspace of V. So here H is a span of v1 v2 and v1 v2 are in R4, a vector space. We have already proved that Rn is a vector space. So we can conclude that H, that is span of v1 v2, is a subspace of R4 by using this statement. Similarly, this is another problem. Let W is equal to span of v1 v2 and so on vp, where v1 v2 and so on vp are vectors in vector space V. Show that vk is in W. Vk is any randomly chosen element from these vectors. For k less than or equal to 1 less than or equal to k less than or equal to p. We know that span of v1 v2 and so on vp is equal to set of c1 v1 plus c2 v2 and so on c2 vp. such that C1, C2, C3 are scalars. This is the definition of span. And using this definition, we can write V1 as V1 is equal to 1 V1 plus 0 V2 plus so on plus 0 V2. I have chosen the set of scalars such that the multiple of V1 is 1 and remaining are zeros. So now V1 is a linear combination of all those vectors, all those P vectors. So V1 is in the span of those vectors, those P vectors. So that is nothing but W. So V1 is in W. Similarly, this argument can be continued for any vector in that set. So for any 1 less than or equal to k less than or equal to p, the vector vk can be written as vk is equal to 0 v1 plus 0 v2 and so on, 0 vk minus 1 plus 1 vk plus 0 vk plus 1 and so on, 0 vk. So all the scalars are chosen as 0 except that vector itself, that is taken as 1. That scalar is taken as 1. So each vector in this set can be represented in the same manner. So each vector is a linear combination of other vectors. So all the vectors starting from Vk to Vp are in W. So at random, we can say that Vk is in W, where 1 less than or equal to k less than or equal to p, which is a spanning set. W is a spanning set of V1, V2, and so on. Let us move on to one more problem. Let H be the set of all vectors of the form of a matrix minus 2t, 5t, 3t. Find a vector v in R3 such that H is equal to span of V. So we need to find a spanning vector for this set. And we have to show that why this H is a subspace of R3. It is the given hypothesis, of course. So this can be written as minus 2, 5, 3, the column matrix multiplied by T. T is taken as common. It is taken out of the matrix. So this is our required vector. So if V is equal to minus 2, 5, 3, then V belongs to R3 since it has 3 components. And now H can be written as this thing is replaced by V. This can be written as V. This is denoted by V. So this is Vt. T belongs to R, which is nothing but a linear combination of V, single vector, that is span of V. So this is the required V. This is the vector spanning the set H. Further, as per our previous statement, we know that if V1, V2, and so on, Vp are vectors of the vector space V, then spanning set of V1, V2, Vp is a subspace of V. So this spanning set H is the subspace. This is the reason why H is a subspace. Let us move on to one more problem. Let H be the set of all vectors of the form 3t, 0, minus 7t, where t is any real number, so that H is a subspace of R3. So this is the given hypothesis. This can be written in this form. T is taken common again. If V is equal to this vector, column matrix 3, 0, minus 7, Then since it has three components, it belongs to R3, and H can be written as Vt such that T belongs to R. So it is a linear combination of V only. That's why it is a span of V, where V is this one. So again, by our previous statement, we can say that H is a subspace of this R3. Since the vector chosen is a vector of R3, R3 is the vector space here. That is why H is subspace of R3 using this previous statement. Similarly, we can go ahead in the case of 4 entries also. So this is the given hypothesis. This can be written as this. Here we have two scalars, 2s plus 4t. So this can be written as s times 2, 2, 2 and 0. 0 in the last column. There is no s component here. Similarly, this is t times 4 is here, and there is no t term in the second row. That's why it is taken as 0, and minus 3 and 5, such that st belongs to R. This column matrix can be written as the combination of these two vectors. So now this is my V1 and this is my V2. So using those V1, V2, we can see that there are 4 entries in V1, V2. That's why V1, V2 belongs to R4. So now W is set of SV1 plus TV2, such that ST belongs to R. So we can write it as it is span of V1, V2. So again, from our previous statement, if V1, V2 and so on Vp are vectors of a vector space V, then span of set of V1, V2, Vp is a subspace of V. So by using this statement, we can say that span of V1, V2, which is denoted by W here, is a subspace of R4. R4. So in this way, we can conclude that with a single step, we can show that it is a subspace. We have to show that the given set is spanned by some vectors of vector space. That is enough to show that it is a subspace of the given